Okay, so complex numbers. So a little history with a complex number is basically people are working with square roots trying to solve quadratic equations, and they would end up with something with a square root with a negative and didn't know what to do with it. Because the definition of the square root is that whatever's inside the square root. So if you have this kind of color code here, the square root of something equals something on the outside. That means that if you square whatever is in the outside, that gives you what's on the inside of that square root. Basically, the square root, whatever's inside the square root is something that's squared, and the square root undoes it. So we have this definition of the square root and what this means. And when you have something with a negative inside, like the square root of 4, you're saying, okay, what squared gives me negative 4? And that's where you have a problem, because the thing squared has to be multiplied by itself to get a negative 4. So if I go with my color coding, so like 2 times 2 gives you positive 4, and negative 2 times negative 2 also gives you positive 4. There's no way to get a negative, because that would mean they'd have to be opposite in sign, and then that's not what it means to be squared. Because to be squared, they have to be the same thing. So people were stumped about this, because they're like, this is coming up in the equations. What do we do about it? And so I forget who it was exactly that came up with this definition, but they were like, well, obviously there are solutions to these problems. We just need to define what it means to be the square root of a negative. We need to call it something so we can do the math. So someone decided, well, let's make the definition that if you have the square root of negative 1, we're going to call that I, imaginary number. So some people think that that's called an imaginary number because the numbers they're working with before were called real numbers, and the opposite of real is imaginary. Some people think it was called imaginary because people didn't believe these things really existed. The truth is they do. Complex numbers come up all the time in electrical currents for alternating current. So anything that is AC, like voltage, anything that that kind of stuff uses imaginary numbers, and that's the only way it works out. So this is a real thing. It's not like imaginary. It actually is a real quantity that makes a lot of things in the world work out, and without this we wouldn't have electronics at all, because we wouldn't be able to do anything with alternating current. So it's really important. It has a very misleading name. And that's sort of why it's been expanded to call it to beyond just an imaginary number, but we have what are complex numbers. And a complex number is where you have a real part plus an imaginary part. So technically, everything is considered a complex number, because our regular numbers we deal with are considered complex numbers with a 0 imaginary part. So, and it's called complex just because it's got these 2 different parts. Some people might say, oh, it's complicated, hence complex. However you want to look at it. But a complex number has both a real part and an imaginary part. And when you work with complex numbers and you do any math with them, you can think of it in terms of treat it like a variable until the very end. You treat it like a variable until you get to something that's I squared, and you replace it with negative 1. And anytime you see something squared, I squared, you replace it with negative 1, and then you continue your math. But otherwise, all the rules are the same, and it's usually easier for a lot of people to think of it as a variable, because then they're like, oh, I know how to work with these things. So going back, to my first example where we had the square root of -4. So we have the square root of -4, and how it works once we have this imaginary number defined is that this is the square root of -1 times 4. And our rules of radicals say that you can split that up into two separate square roots. And then the square root of -1 is equal to I, and the square root of 4 is equal to 2. So you can think of it as I times 2, or we usually write it as 2I, where the I is in the back. So basically, the way you can think about it is if you're taking any square root with a negative, just pull the negative out by turning it into an I, and then you just work with your square root of whatever's left over. And so I'm going to, I'm probably going to end up having, okay, I know that's not going to be prime. So let's say we have the square root of -150. We're basically going to remove the negative by making that I go out in front, and then you have the square root of 150. And once you have that square root of 150, now you can simplify the 150. So if I do it like a factor tree, 150 is 15 times 10. 15 is 3 times 5, and those are both prime. 10 is 2 times 5. So I can rewrite this, and it's a square root, so I want to pair them as 5 squared, because I have two 5s there, one here and one here, and then times 3 times 2. So I've rewritten my 150 in terms of a product of primes, which I know we did a little bit of this when we were looking at greatest common factor before. We did this with fractions. Doing this comes up a lot. It's a very, very handy skill. And then I'm going to use the same rule where I can split up things that are multiplied together inside a square root so that they're outside, or they're separate square roots. And I'm going to put everything that's squared together and then put everything that's left over separately. So then we have the square root of 5 squared, and that square root cancels out the square, so you're left with just 5. So we put the 5 in front of the I, and then 3 times 2 is 6, and so that stays inside the square root. So when you're working with radicals with negatives or square roots with negatives, the first thing you do is pull out that negative, and then the radical gets simplified just like everything else gets simplified, just like regular radicals. It's just you got this one additional step that you have to do when it's involving a negative. And we always pull that negative out first, just for consistency's sake, because there are certain situations. So let's say I have the square root of 4 times the square root of, or the square root of -4 times the square root of -2. This kind of problem can cause issues because some people will say, oh, well, I can recombine those into one square root and do the square root of -4 times the square root of -2 and get the square root of 8. Which I'm going to just skip to the simplification, and that is 2 times the square root of 2. Now, if you do it the other way, where you pull out an I first, you would have I times the square root of 4 times I times the square root of 2. And you can treat the i's like variables, so you can multiply those together. So an I times an I is an I squared. And then I can multiply those square roots. 4 times 2 is 8. And then I squared is equal to -1. So you have -1 times the square root of 8, and you end up with a -2 times the square root of 2, because the square root of 8 is square root of 2, or 2 square root of 2. You have a contradiction here. You actually get the same answer but opposite signs. So mathematicians had to make a decision, which way do we do this? And so this, where you pull the I out first, that is the correct method, so that everybody is consistent and gets the same answer. So the I always has to be pulled out first so that you can get rid of the negative inside the square root, and then everything else goes forward and you do the rest of the math. So you want to be careful about that. And that's one of those things where it's like, well, according to our rules, either one works, so we just had to make a decision on the proper method so that everybody gets to the same spot. So now that we've seen a little bit with just the imaginary unit and square roots and negatives, let's look at complex numbers when we're adding them, subtracting them, all that kind of stuff. So let's say I'm going to just make up some problems here. We have one complex number, 2 minus 5i, and then I have a second complex number, 7 plus 3i. So treat a complex number, treat those i's just like they're variables. This is literally just 2 minus 5i plus 7 plus 3i. Add your like terms. 2 plus 7 is 9. Negative 5i plus 3i is negative 2i. That's your answer. That's your answer in complex number form. And it's the same thing if you were subtracting. If we had the same numbers and I was subtracting them, first, we're just going to follow our rules. You distribute the negative through the parentheses. So this is 2 minus 5i minus 7 minus 3i. Then you add your like terms. 2 minus 7 is negative 5. Negative 5i minus 3i is negative 8i. And there's your answer. There's your complex number. So even though it's an imaginary unit, it follows the same rules. And this is true of multiplication. So let's say I was multiplying these together. 2 minus 5i times 7 plus 3i. So you're going to use FOIL. Anytime we have two things times two things, we use FOIL. So you multiply the first terms together. So 2 times 7 is 14. And then the outside terms, 2 plus 3i. So you multiply the numbers, which is 6. So you get plus 6i. Inside terms, we get negative 5i times 7. So negative 5 times 7 is negative 35, if it will let me write. Why is it not letting me write? There we go. And then the last terms, you have negative 5i times 3i. So negative 5 times 3 is negative 15. I times I is I squared. So we will start by adding like terms, the 6 minus 35. So 6 minus 35 is negative 29i. And then we have this minus. It really, for whatever reason, my screen has decided that I can't write on the bottom half. Don't know what's going on there. Then we have negative 15i squared. Now this is where things are different from working with variables, because instead of just having leaving it like this, we have something special, that I squared is equal to -1. So we're going to rewrite this. I don't know why that one part of the screen it does not want me to write on. -15, and instead of I squared, that's times -1. So that actually it ends up becoming a positive 15. There we go. So we get 14 minus 20i plus 15. And then you can add the 14 and the 15 together, which is 29. So we get 29 minus 29i. And we get another complex number. So when you're multiplying these, you multiply it just like anything else. You do the FOIL process, you can distribute, all of those rules apply, but you do have extra steps when you get to the I squared, because that always gets replaced by -1, because our goal is a complex number in the end, and a complex number has a real and imaginary part. There is no I squared part. It's just something with an I and something without an I. So that's like the extra step that you have to do here. So that's multiplying. Dividing is a little different, and that's where things get a little tricky for people. And so I'm going to write the division as a fraction here. So when we're dividing here, we don't really have, I mean, it's like, what do? You don't have a single thing in the denominator. You can't just divide them by a number. So we do this thing that's called rationalizing the denominator. And that's where we don't want to have I in the bottom. So what we do is we multiply the top and the bottom by the denominator, but you change the sign of whatever your term with the I is. So if it's a positive 3i, you're going to multiply by the same thing, but with a minus 3i. If it was a minus 3i, I'd be multiplying by a plus 3i. The key is you want to change the sign there. And this is because then on the denominator, we have a difference of, or we have a sum and difference of a binomial. And when you multiply that together, that gives you the the difference of squares, and the middle term disappears. That's the point here. So we're trying to get it so that middle term with the I disappears. So all we're left with is, like on the left when we multiplied, we have the real term and the I squared term. The I squared gets a -1, so that becomes a real number, and we don't have that I term at all. That's the goal here. So we have to multiply on the top and multiply on the bottom and do FOIL in both directions here. So on the top, I've got the 2 times 7, which is 14. Then 2 times minus 3i, so that's -6i. -5i times 7, which is -35i. And then a -5i times a -3i, which is a positive 15i squared. So you can see it's slightly different from the multiplication on the left because of the difference in signs. So that difference in signs does make a difference there. Now I'm going to multiply the denominator. So I have 7 times 7, which is 49. Then 7 times -3i, so that's -21i. Then we have 3i times 7, so that's plus 21i. So you can see that that middle term is going to cancel because they're opposite in sign. And then 3i times -3i is -9i squared. So now I'm going to start simplifying. And once again, you can see that like that bottom part of the screen, like the computer's just decided that you guys don't get to see anymore. Don't know what the deal is there. So I'm going to combine my like terms. Oh, hi Windows, go away. So I've got 14. Then I have negative 6i minus 35i. So that's negative 41i plus my 15i squared. In the denominator, I have 49. The minus 21i and the plus 21i cancel out, and then I have minus 9i squared. So now everything with an I squared, both on the top and the bottom, I'm going to replace with negative 1. So I have 14 minus 41i plus 15 times negative 1. And then 49 minus 9 times negative 1. And then I multiply those negative 1s, so I'm basically just changing the sign. So we have 14 minus 41i minus 15, and then 49 plus 9. So now we have more like terms to add. So 14 minus 15 is negative 1. And then 49 plus 9 is 58. So we now don't have an I in the denominator anymore. But we're not done because we generally don't leave our complex numbers this way. We want to write it in what's called standard form, where you have the A and the B parts separated. You don't have a single fraction here. So to do that, all you do is take each thing on the top of the fraction and write it over the denominator, and then simplify it if possible. So I don't think 41 is prime, so this definitely doesn't simplify. So I'm going to just rewrite this. Now I made up this problem, so that's why I got kind of gross fractions here. But we usually want to rewrite it so that there's separate fractions out so that it's in standard form for a complex number.